Okay, so section 4.2 deals with finding maximum and minimum values. Okay, and they comment here, they comment that some of the most important applications of differential calculus are optimization problems. Okay, there are books on optimization. An optimization problem is when you're required to find the optimal or best way of doing something. Okay, so an example would be like, let's say you had a certain, well, they actually have some examples here. What is the shape of a can? What is the shape of a can that minimizes manufacturing costs? So, for instance, you might want your can. Maybe you're designing a can to hold soda, and you want to have your can hold a certain volume of soda. So, how high should the can be? How wide should the can be so that it holds the soda, but minimizes the amount of, metal or aluminum used to make the can? That's an example of an optimization problem. All right. Another one, what's the maximum acceleration of the space shuttle? It's an important question for astronauts who have to withstand the effects of acceleration. Okay. What angle should blood vessels branch so as to minimize energy expected by the heart in pumping blood? Okay, so this is a medical application. So all these problems deal with finding maximum and minimum values of a function. And what I want to do is give you a guided tour for the first, maybe 4 or 5 examples in the book. We're going to look at some figures, and then we'll do a few problems. Okay. So they give definitions about what an absolute maximum is and an absolute minimum. Okay. And then they give a definition, and don't copy it down. Don't copy it down. This is because we're going to be these definitions, like for instance, they say the absolute maximum value of a function on a domain is going to be if f of c is greater than or equal to f of x for all x in the domain. So that's like a formal definition, and that's fine, but I think that it's very helpful for students to see examples and then when you see the examples, it'll reinforce the definitions. So we have, when we are doing an optimization problem, we're looking at some function that models a situation, and we want to find maximum and minimum values. That's really that's why we're talking about maximum and minimum values. And you can have absolute maximums, absolute minimums, but you can also have what are called local maximums and local minimums. Okay, local maxes and local minimums. Okay, so like for instance, in this figure here, figure 2, they've drawn a picture. They've drawn a picture of this pink function, purple function here. Okay, and it is a function because it passes. It's not a pretty function, but it does pass the vertical line test. I mean, it is a function. Is there any value, by the way, where this function would not be differentiable? Looking at A, B, C, D, E, is there any value where the function would not have a derivative? That's right, Lynn, that's right, Ian, C. Because at when x equals c, there's a cusp there. Okay, so you've seen that before. Well, all right, so they're saying that so the function, they limit the domain of it. Well, I want to be a little bit careful. They in the picture, think of the picture as the function. the absolute minimum value of the function is f of a. Okay, the absolute value of the minimum function is f of a, because that when x equals a, I mean that the function is lowest at x equals a. Oh, now where's the function highest? At what value of x is the function highest in the picture in figure 2? So we have that. That's right. That's right. In x equals d. That's right, Chucko. When x equals d, the function is highest there. Okay, so that's an absolute max. Okay. Now you have other values where you have local minimums, okay, and local maximums. So when x equals c, the function has gone down, and then after c it goes up again. So it's a little valley there, you know, bottom of a hill, funny kind of hill, but it's the bottom of a crevice. C is a local min, but it's not an absolute min because f of a is lower than f of c. F of e is another local minimum. Okay, it's not the absolute min though. And then we have local maxes, f of b and f of d. Now, f of d, by the way, is also an absolute max. But in the neighborhood around d, f of d is considered a local max in that neighborhood locally. Okay, so I'm trying to sort of, I'm not trying to steer you away from the definitions, but I want to use, because definitions are important, but I want you to get an intuitive feel for what absolute mins and max are and what local mins and maxes are. They have, and then the definitions will be easier. Like here in figure 3, they have a nice little picture here. A nice little picture. So in figure 3, you can see the local min and local max. So like around x equals 4 in that area, the x equals 4 is the local minimum. And around at x equals 8, around that area, the local maximum is at x equals 8. But at x equals 12, that's going to be a local and absolute minimum because it's a local minimum. But also the function after x equals 12 in figure 3, the function is going to rise based on what they're showing. And so, see, well, yeah. So I want to just try to kind of keep things simple. But are there any questions so far? Incidentally, Lynn's good, very good, very good. What do you notice about in figure 3, the local min and local max? If you think about the function and you think about tangent lines, all right, at x equals 4, the local min, what's the slope of the tangent line to that function at the local min at x equals 4? What's the slope going to be? Okay, I'm hearing a few answers here. At x equals 4, think about the tangent line to the function, to that blue function. What's the slope going to be of the tangent line? The tangent line is going to be flat, right? So what's the slope of a flat tangent line at x equals 4? 0. That's right. That's right, everybody. It is 0. And what about at x equals 8? There's a local max at x equals 8. What's the slope of the tangent line to the curve at x equals 8? Well, it's also 0 because the tangent line is flat. So there's a theorem called Fermat's theorem that states that if you have a local maximum or minimum, then the slope or the derivative at the value of the local max or minimum has to be 0. Local maxes and local minimums, the tangent lines are going to be flat. And so flat tangent lines mean, I mean, it has to be. Just think about it. Just think about it. I mean, is there any way that, I mean, if you have a local max, well, I mean, a local min, you know, the function goes down and then it reverses. So you got to have a turnaround point. Well, it's going to be flat at the turnaround point. The tangent line will be flat there. I guess what I'm saying, let me be, I mean, I think I'm being clear, but let me just use the whiteboard real quick here. One moment. X, Y. Okay, and I'll draw a curve here. Okay, so let's say this is 1, and let's say this is 3. Okay, at x equals 1 for this function f, is x equals 1, is there a local max or a local minimum there? Obviously a local max. And you can, and what you're doing in your mind is you're seeing that, hold on, let me get it right here. You're saying that, hey, I mean, you see the function turning around, but in order for the function, I got to be a little bit careful here. The function goes up and then it switches and goes down. Well, there's a flat that where it does that switch, there's a you know, there's the tangent line's flat. What about when x equals 3? Is that a local min or a local max? It's a local min, and you can see at x equals 3, the tangent line's flat there. All right, so far so good? All right. And this is in the recording, of course. I'll move on, but I mean, is anybody, you don't need to copy this really, but may I move on, or are we? All right, let's move on then. Thank you. So now back to the book. Okay, so they give it, these are called extreme values, by the way. I want to be a little bit careful. Maximum and minimum values of a function are called extreme values. So, like for instance, the cosine, example 1, the cosine function, f of x equals cosine of x. It's going to take on absolute values, local and absolute maximum value of 1 infinitely many times. We know how the cosine curve behaves. Okay, so that function has many extreme values. In example 2, you can have a function with a minimum value but no maximum value. Look at Look at figure 4 here. This parabola, y equals x squared, figure 4, that has a minimum value, and that value is 0, but it has no maximum value. Okay, I mean, you know, pretty simple. Nothing really too tricky here. Example 3, a function with no maximum or minimum. If you have y equals x cubed, okay, that function will not have a maximum or a minimum. Now, even though at x equals 0, at x equals, like y equals x cubed, when x equals 0, the slope, the tangent line to the curve at x equals 0 is flat. The curve doesn't turn around. You know, there's just no maximum or minimum there anywhere on the curve. Not at x equals 0 either. All right, are you getting an intuitive feel for this? All right, and then you can have a maximum at an endpoint. So here they have a function, a polynomial. They're graphing the polynomial, but they're limiting the function so that x is between -1 and 4. They're limiting the domain. Okay, they're limiting the domain. And what they do is they graph this function right here. Okay, and they make some comments about it. Let me highlight it. So f of 1 equals 5 is a local maximum, but the absolute maximum is f of -1 equals 37. Clearly, it's the highest value. But the absolute maximum in this case is not a local maximum. See, got to be a little bit careful here. It occurs at an endpoint. For an absolute maximum to be a local maximum, you have to have well, I'll show you where the issue is. Okay. F of 0 equals 0 is a local minimum, and f of 3 equals -27 is both a local and an absolute minimum. F of 3 equals -27 is an absolute minimum for sure. You see, the problem here at -1, they're saying that you have an absolute maxima at when x equals -1, but you see the. Let me bring up the whiteboard again so you can see this. Should have my phone on mute. It's ringing in the other room. I'm just going to let it ring, okay? All right, one moment. Okay. One moment. Student, thank you. Students, I'm just putting this on silent mode. Just give me a moment here. How many have had a situation where you think you're getting a call? Oh, wow, I'm called today. It turns out to be a robot wanting your money. How many have had that situation? All right, now let me see here. Okay, so okay, one moment. Okay, so I have two different functions here, and let's look at you know, A and B here. So would in A, would the value be a local? I mean, do we have here a local max at in that graph A? I mean, can we say that's a local max? We absolutely can. Okay. Because about a neighborhood of x equals 3, this value at x equals 3 is the highest value. It's in that neighborhood around x equals 3. You know, think of a little interval around x equals 3. That value is a local max. You know, the little interval around x equals 3, that's a local interval, locally. However, at x equals 3, I mean, the function, if I put these, if I do this, would that point also be an absolute max? Would it be an absolute max? Absolutely. Because it's the highest point in the entire function. Okay, I mean, it's absolutely the highest. See, that's how I like to think of it. Okay, but now if we go to figure, and you know, let me put the little interval here just so. Now if I go to figure B, and I'm looking at, you know, the blue point there, is that a local max? Would that be a local max? Well, can I put an interval around x equals 3 and say that that point is the highest on that interval? I can't, right? Because I don't have an interval. It's an endpoint. That blue point there, that blue point is an endpoint. So I don't have an interval that I can surround 3 by. So I can't say it's a local, I can't say it's a local max. Okay, but it is an absolute max. How many find this example? Is this example helpful for you to see the difference? Are we good? Good. Now, you know, the book will have its definitions and all that good stuff, but you know, you're welcome, Sebastian. You're welcome. Absolute max only. Okay, so anytime the highest or lowest value of a function occurs at the endpoint, at an endpoint of the function, it can't be a local max or min. All right, are we good? Shall we move on? Are there any questions? All right. All right. Okay. So let's go back to the book. Let's go back to the book. And the book talks about something called the extreme value theorem. And that's nice. Let's use some graphs to help us get a feel. We know what extreme values. We have a feel. Let's look at this figure here, figure 8. Okay. See, I'm trying to get you an intuitive feel for things. And then we can always then look at the definitions to the figures will intuitively help you understand the theorems, the definitions. But it says here in figure 8, this function has a minimum value. Okay, this function has a minimum value in figure 8, f of 2 equals 0, but it has no maximum value. Okay. It has no maximum value. Isn't f of 1 equals 3 a maximum value in this figure 8? Whoops, hold on. I don't know how that happened. Okay. Wait, where'd my thing go? Hold on. All right, hold on, class. I'll get it back. Don't worry. I mean, what's the problem? Why is there no maximum value? Looks to me like the function is highest when x equals 1, but yet it says there's no maximum value. Why would that be? Does f of 1 equal 3 in the picture? Okay, does f of 1 equal 3? Let me see here. Hold on. Hold on, let me go back to the... Hold on, isn't it sharing? Hold on, is it not? Hold on, class, is it not? Are you seeing the figure here? Are you seeing it? I'm not seeing it in the... Okay, white screen. Hold on. Let me get back here. I don't know what happened here. Hold on. A moment. Okay. Now, can everybody see the figure okay? So, thank you. So what's going on here? I mean, f of 1 equals 3 is not a maximum value? Why not? Does f of 1 equal 3 in the picture? Why not, Sebastian? It does not. There's a hole there. That's right, John. When x equals 1, there's a hole. Well, I mean, it's discontinuous at x equals 1. But f of 1 doesn't equal 3. It equals, whatever's that right, whatever that red dot is. Maybe it's like 1.5 or something like that. So, all right. There's no, all right. Well, what about this though? Couldn't the maximum value be like 2.99? I mean, couldn't the maximum value of the function be 2.99? I mean, the function does get pretty near x equals 1. The function does get pretty close to 3. So could the max? Oh wait, hold on. But Sua says no. It could be 2.99999. Oh, but maybe it isn't 2.99999. Maybe it's 2.9999999. Oh no. Maybe it's and so on and so on and so on. You see, there's no maximum value. No maximum value. You see, so this really demonstrates the extreme value theorem, because, well, it shows you why the extreme value theorem doesn't apply, because you have a discontinuous function. But the extreme value theorem says if the function is continuous, okay, if you have a continuous function on a closed interval, then f will attain an absolute maximum value and an absolute minimum value somewhere on that interval. It has to, because it's continuous. But in this example, figure 8, we didn't have a continuous function. Now, figure 9 says this function has no maximum or minimum. Well, we know it doesn't have a minimum because when x equals 0, the function's not defined. There's a hole there. But what about the right side? What happens as x approaches 2? What happens to the function? In figure 9, when x approaches 2, what's this function doing? What does it look like the function has at x equals 2? That vertical dashed line, that appears to be a vertical asymptote. So that's right, Lynn. And so the function's going to keep going up and up and up. It's never going to stop. It's not, the function is not continuous on 0, 2. Okay, it's not continuous because when at x equals 2, the function's not defined there. It's not continuous there. So these are just some examples, these are just some examples. And hopefully it's fairly intuitive. They talk here about something called Fermat's theorem. We actually talked about that. If you have a local maximum or minimum at a point C, okay, and if the derivative exists, then f prime of C equals 0. From figure 10, it's pretty clear there. Okay, so when I think we're probably ready to look at some examples, but are there any questions? Oh, how do you prove that? They mention here, our intuition suggests that Fermat's theorem is true. A rigorous proof is given in Appendix E. So in your book, in Appendix C, there is a rigorous proof of it. I'd actually like to get to some examples. but you could definitely, who chatted that question? That was a good question. Yeah, intuitively it seems true. And Ian, you can check Appendix E and check it out. It might be worth your time there. And I think we're probably ready for some examples. Usually they talk a little bit about who the Fermat's theorem. It's named after Pierre Fermat, but I don't see where the the biography is. Usually there's a little biography. Oh yeah, here we are. Fermat's theorem, which says that if you have a local maximum or minimum at a value c, then f prime of c, and if f prime of c exists, then f prime of c equals 0. It's named after Pierre Fermat. Look when he lived, 1601 to 1665. A lawyer who took up math as a hobby, there's a whole course on mathematics history. It used to be offered at our college, but I don't think it's offered anymore. But there are books that are all about inventors of mathematics. But let me go ahead here and bring in a few examples here. So one moment. One moment, class. One moment. I have to upload. I'll be just a moment. Okay, I should have it now. Let me bring it in. One moment. Yep, there it is. All right. All right, so we're going to do a few examples. I mean, it's nice to look at graphs and get an intuitive feel. But now I think we should look at a few functions just to, just so that, the goal here is going to be eventually being able to graph functions at a very in-depth level, a level you've not seen before. You've graphed functions your whole life, but we're going to talk about things like concavity and so forth, things that you aren't aware of. But with calculus, we can do these things, but we have to start in the beginning here. So here's an example from section 4.2. What we want to do is we want to find what are called the critical numbers of this function. Let me give you a moment to copy it down. One moment. Okay, so you notice I'm not doing a problem with the polynomial, right? The polynomial would be, I mean, that's easy enough to do, but I want to do this one. So now this function, you see, this function here is a function that you might have, like in pre-calculus, a somewhat difficult time graphing it. I mean, what if you had to graph this function, the f of x equals x to the 3/5 power times 4 minus x? What if you had to graph that and, you wanted to do it without a calculator? Okay. Could you do it? Well, you can, knowing calculus. And knowing calculus, too, there are things you can learn about the function that the calculator can't tell you, because, well, you'll see. Or, so, all right. What I mean is it's sometimes difficult to see on a calculator certain behaviors of a function. But knowing calculus, you can understand the behavior from a fundamental level. But you'll see that later on. Right now, what we want to do is find the critical numbers. So the critical numbers are where any critical number C, by definition, f prime of C equals what for a critical number? If C is your critical number, okay, if C is a critical number, that's right. That's right, Ian, that's right, Matsua. If C is a critical number, then f prime of C equals 0. But hold on. Also, a critical number is also where f prime of C does not exist. So let's go to the next. I mean, I actually have that written down. This is a definition in the book. Okay. This is a definition in the book about what a critical number is. And a critical number, it's actually definition 5. A critical number of a function f is a number C in the domain of the function. It has to be in the domain of the function such that f prime of C equals 0. So those critical numbers would correspond to local maxes or local minimums when f prime of C equals 0. Or, okay, that's one type of critical number. I want to be careful here. So critical number is a number of a function f, the number C in the domain of the function f such that f prime of C equals 0. In that case, that would identify local maxes or local minimums, or value C where f prime of C does not exist. That's also, C would be a critical number. And, I guess I never thought why they called those critical numbers. I guess I would view it as in order to understand how the function behaves, it's critical to find those values. Okay, that's how I would view it, because it is. So okay, so what we have to do is we have our function f of x equals x to the 3/5 times 4 minus x. We have to take its derivative. We have to take the derivative of f. And so what rule are we going to use to take the derivative of our function f? Good, the product rule. That's right, got to use the product rule because we have two functions here. Good. Okay, and so I do that. Okay, the derivative of x to the 3/5 is, by the power rule, 3/5 times x to the negative 2/5 power. And then I leave the 4 minus x alone. And then plus, I leave x to the 3/5 alone. And then I take the derivative of 4 minus x, which is negative 1. So it's no problem taking the derivative. But here's what you have to do, what you have to learn to do, is in order to identify the critical numbers of the function, you have to write the derivative in factored form. Or put it this way, it's very helpful to write the derivative in factored form. Okay, and you want to do this, you don't want to really look at the graph of the function f. You want to do this without looking at the function, without looking at it on the calculator. Kind of regard that as cheating a little bit. You know what I mean? Like, try to get your critical values without looking at the picture of the graph, because that's really very important to be able to do. Because graphs don't always tell you everything. Believe me, you'll see. So what I'm going to do is, how many remember problems where it says, hey, write your answer in terms of the positive exponents? How many remember doing problems like that? Maybe in pre-calculus or algebra, write your final answer in terms of positive exponents. Okay. Hey, why'd you have to do that? Here's an example that'll show you why. Thank you, everybody, for your input. I'm gonna write the first term here in my expression as 3 times 4 minus x over 5 times x to the 2/5. So my derivative now is equal to this, the difference of these two expressions. But it's not in factored form. I have to get it in a more convenient form to identify the critical numbers. So what I'm going to do is, since I have a fraction on the left here, I want a fraction on the right. Well, x to the 3/5 is x to the 3/5 over 1. If I look at the denominators, okay, the 5x to the 2/5 power and the 1, the least common denominator is 5x to the 2/5 power. And so what I'll do is, I have that on the fraction on the left, but on the right, I'll multiply the numerator and denominator of x to the 3/5 by 5 times x to the 2/5. And then that's going to get me then the common denominator, 5 times x to the 2/5. And then I can combine the numerators as you see I've done here. Okay, and I would be looking for this on your next exam. I look at your work. Okay. Now 3 times 4 minus x is 12 minus 3x. So I can write my derivative as then, 12 minus, incidentally, x to the 3/5, like in the step above, x to the 3/5 times x to the 2/5 is x to the 5/5, right? The 1 there is because I'm going to have, when I add the exponents, I'm going to have 5/5, which is 1. Okay, and so f prime of x equals 12 minus 8x over 5 times x to the 2/5. Are there any questions so far? this form of the derivative is a form that I can work with, because here I can find the critical numbers. I can find the critical numbers. Okay, so let's go ahead to the next page. If we're good, we'll move to the next page. Let's see. Ian says, don't they have different bases? You mean, Ian, this part here when I take, well, what I'm doing is the 5 is not part, so Ian's asking about when I take x to the 3/5 and multiply it. See, I'm letting the 5, I'm not, the 5 isn't involved with the x to the 2/5. So, okay, good question, good question. Okay, so now f prime of x equals 12 minus 8x over 5 times x to the 2/5. When the derivative is in this form, I know that the derivative will equal 0 when x equals 12/8. And why is that? Because if the numerator equals 0, the derivative will equal 0. So if you set 12 minus 8x equals 0, 12 will equal 8x. And so x will equal 12 over 8, or 3/2. Also notice that f prime of 0 does not exist. F prime of 0 does not exist because if you put 0 in the denominator here, 0 to the 2/5, you'd get a 0. And you can't have a 0 in the denominator. So a critical number of a function f is a number c in the domain of the function such that f prime of c equals 0 or f prime of c does not exist. Well, 0, x equals 0 was in the domain of the original function. The original function, remember, was f of x equals, hold on, x to the 3/5 times 4 minus x. So even though the derivative is not defined at x equals 0, the function is defined. Got to be careful here. The function is defined at x equals 0 because 0 to the 3/5 is okay. It's okay. That's going to be 0, right? So what they do is in the picture below, and I decided to include it in the recording. This is actually from example 5, this example I'm doing. But the figure 13 below shows a graph of this function. This function, x to the 3/5 times 4 minus x. And you can see that when x is, they graph the function f. You can see when x equals, here's 1, here's 2. When x is 3/2, okay, when x is 3/2, f prime of 3/2 equals 0, right? Tangent line slope is 0 at x equals 3/2, right? This is 3/2 here. And at x equals 0, well, you can see the function is basically has it isn't an asymptote because the function is defined at x equals 0, but the slope is like positive infinity at x equals 0. It's undefined. Okay, so you have two critical numbers. X equals 0, the vertical tangent there, and horizontal tangent when x is 1/5. So x equals, sorry, 1.5, 3/2. So x equals 1.5 and x equals 0 are critical numbers. Okay. But you see, like an example, what I was talking about is like this complicated function here. If you drew that function on your calculator, would you really know that there was a that there's a vertical tangent at x equals 0? Would you really know that? You know, would you be able to say that? You'd say, oh yeah, at x equals 0, the slope of the tangent line to the function at x equals 0 is very steep, but you know, would you know that it's a vertical tangent? I'm not sure you would, you know. And calculator can't give you all the information, you know. So you're really looking at functions now at an in-depth level, the graphs, their behavior, you know, and you need math to understand that in-depth behavior. Are there any questions on this? How many think this is kind of cool, what you just learned about critical numbers? Okay, thank you, Lynn. Yeah, I'd like maybe a few, it'd be nice to have a few thumbs up for the recording. I don't know. I hope maybe somebody else likes it besides Lynn. Okay. Oh, Joe, he's not a fan. Okay. Well, at least Joe's giving his input. Okay. All right. Betsua likes it. Thank you, Betsua. All right. Thank you, Kelvin. John says once he's got his mind wrapped around the concept, completely understand. And the 4.2, you're going to have the section 4.2 will be broken up into several assignments. The first assignment will be due this Friday. So like this Wednesday, we'll do another example of a few more examples from 4.2. Okay. All right. But what I'd like to do now, I want to give you some. Let me stop the recording.